regardless of the experience and careful planning that have gone into drilling a well, things can still go wrong. Other, less dramatic events can also occur that can impede progress. They include differential sticking, hole caving, twist-offs, fishing, and lost circulation. Let me explain each of these in more detail. Pipe that gets stuck in the hole is called stuck pipe and is a constant concern. When this common problem occurs, it is usually quite simple to resolve so that the drilling program can resume. In extreme cases, however, where efforts to unstick the pipe is unsuccessful, the portion of the hole with the stuck pipe must be abandoned, adding cost to an already extremely expensive operation. Therefore, the driller tries various procedures to free stuck pipe. Let's look at some. Differential sticking is probably the most common cause of stuck pipe and occurs most frequently when drilling into softer, unconsolidated formations typical of continental margins. Differential sticking happens while penetrating permeable formations under overbalanced conditions. Some of the liquid in the mud is forced out into the formation, leaving behind the mud solids as a filter cake at the formation face. If the pipe rests motionless on the side of the hole too long while making a connection, it can become differentially stuck. When a pressure differential is created between the mud column pressure on the inside of the hole and the formation pressure on the outside, the pipe is pressed against the side of the hole with such force that the pipe cannot be moved. To keep differential sticking from occurring, the driller tries to keep pipe moving in overbalanced pressure conditions at all times. Hole caving is another drilling problem. Here, the side of the hole caves in, causing the pipe to become stuck. There are many reasons for cave-ins. Here are three common ones. Number one, absorbing the mud filtrate, some shales swell up and slough off their outer layers into the well. Number two, large quantities of material from uncemented or fractured formations fall into the hole. Number three, the weight of the overlying rock force or squeeze out salt and plastic shale formations into the well bore. Once the pipe becomes stuck, for whatever reason, it is necessary to free it. The cause for the pipe becoming stuck in the first place must be found. If the pipe is differentially stuck, then the first approach would be to reduce the weight of the mud and eliminate the overbalance. Of course, this is only possible if there are no concerns about a permeable zone kicking. If reducing the mud weight and eliminating the overbalance is not possible, then another approach might be tried. Here, if mud circulation is still possible, then a few barrels of refined oil or mud cake solvent might be circulated down the pipe and then up the annulus until it's over the stuck area. Thus, by keeping the tension and torque on the pipe with this fluid, it may be enough to free the stuck pipe. If this approach fails, it may be time to run a free point indicator down the drill string by wireline. In this approach, tension is pulled on the drill string while the free point indicator locates the point below which the pipe is not in tension. Identifying exactly the spot below which the pipe is not in tension as the place where the pipe is stuck allows for a light explosive to be run down the inside of the drill pipe and detonated immediately above the free point. Hoping that the explosion will rattle loose a coupling so that it can be unscrewed, the string is then carefully rotated counterclockwise in an attempt to break the rattled coupling. Once unscrewed, the string is pulled out, leaving the fish or bit and the stuck part of the drill pipe still in the hole. The drill string is then reinserted with a set of jars or devices that deliver sharp blows. Once in place, the jars are activated, sometimes repeatedly, delivering downward hammer blows to the stuck pipe. In most cases, this approach is successful and the stuck pipe can be quickly dislodged and recovered. If this method fails, however, a wash pipe can be run to wash over the outside of the fish, hoping to remove the material that is causing the stick. As you can see, different procedures are tried with the hope that one of these will free the unstuck pipe, but, like I said before, if all attempts fail, then that portion of the hole with the stuck pipe will have to be abandoned. Now, let's look at another type of drill pipe failure, called twist-offs. They occur from metal fatigue during routine drilling operations. If twist-offs occur, the first half of the broken pipe is brought to the surface, and then, for the piece still in the hole, it is necessary to fish it out. Let me explain. As I said, first, the movable portion of the broken pipe is brought back up to the surface so that the condition of the pipe or fish and the break can be examined and analyzed. Next, an impression using soft metal is made of the piece still stuck in the hole to provide a better picture of its degree of distortion and ruggedness. The impression block can also indicate whether the fish is standing upright or is leaning over against the side of the hole. The process of retrieving the stuck pipe is called fishing. Depending on the raggedness and position of the stuck pipe or fish, this fish may be able to be pulled out straight away, or it may need to be dressed off or cleaned up. A fish can be pulled out with either an overshot that fits over or swallows the fish if it is standing up clear of the side of the hole, or a spear which hooks or fits down into the fish if it is not. Overshots are preferred to spears because spears can be difficult to remove if the fish is still stuck. Both overshots and spears have multiple grapples that can grip the fish securely, and once gripped, then uses jars or hammer-like blows in hopes of freeing the fish. Lost circulation is another serious problem. It is the result of hydrostatic pressure being higher than the formation pressure in an extremely overbalanced condition. The mud weight fractures the formation rock, creating large channels, causing the mud to flow rapidly out of the wellbore into the rock. This results in an expensive loss of mud and can damage the formation. Let's review. When discussing procedures like drilling ahead, making a connection, round tripping, and the advancements in automated drilling, it is clear that even with sophisticated tools and technology, drilling for oil is a complicated affair. In addition, because procedures can go awry when pressure and temperature conspire to cause blowouts, and where pipe gets stuck or where twist-offs or lost circulation can occur midway through drilling, it is little wonder that scientists and engineers work relentlessly to help improve procedures and solve problems like those mentioned above so that oil and gas can be brought to market more efficiently and cost-effectively and under ever-increasing hostile conditions today. Two relatively recent advances over the last several decades have expanded the ability of the industry to extract more oil and gas in places that were previously inaccessible. First, directional drilling and its offshoot, horizontal drilling, have revolutionized the way drilling is done. Directional drilling was first developed when the industry moved offshore. Prior to that, wells were drilled vertically or relatively straight down. When drilling was exclusively on land, a rig could more easily and cheaply be moved to a new location to drill another vertical well. Offshore, especially in deep water, however, the cost of building another offshore platform in another location every time a new well is needed to be drilled proved to be prohibitive. The industry, therefore, developed specialized tools to perform directional drilling so that they could drill multiple wells using rigs on the same platform. Today, this technology has advanced to the point that directional and horizontal drilling have replaced traditional vertical drilling in many instances. Let me highlight the areas where directional drilling has proven to be most beneficial. Directional drilling has been used, number one, where vertical drilling is not possible due to above-ground restrictions imposed by mountain ranges or public parks or the presence of existing structures like buildings, dams, bridges, etc. Number two, when multiple wellheads can be grouped together in one location. Number three, when relief wells need to be drilled to relieve pressure on another well to extinguish a burning blowout. Number four, when multiple target zones must be drilled. Number five, and when sidetracks are needed to drill around obstructions like a lost string of pipe. Let's look at how directional drilling is done. As this illustration shows, directional drilling typically follows different configurations. It starts with a continuous build, holds, then drops off to form an S-shaped profile. As technological advances in directional drilling have increased accuracy while decreasing costs, the typical configurations are now drilled, for example, using the bent housing motor. The bent housing mud motor allows the bit to be tilted and steered into a preferred direction, thus allowing a directional well. In an S-shaped directional drilling profile, the initial section of the well is drilled vertically. When the area where the hole needs to be slanted or where the kickoff depth is reached, the bent housing mud motor is activated. The pipe is not rotated during this phase. The bent housing mud motor only turns the bit, making hole. The bent housing angle can be set and the drilling proceeds until the built angle is achieved. Once the initial deflection angle is obtained, then the angle is maintained as a straight line to the target zone. If an S-shaped well is required, casing is set into place and a new and smaller bent housing mud motor is used to set up the build drop angle, returning the well to a vertical position. It is this bottom hole assembly, BHA, that permits directional control. By using a magnetic insert in the bent sub-housing, the BHA can be precisely oriented to the target area while surveying the inclination of the borehole regularly.